So my name's Bjorn, and I'm going to talk to you guys today about reactive programming for distributed authentication. So just a little bit about myself and Workday. I'm a software engineer working on the platform security team at Workday. And the focus of my work is on authentication and federation services, things like SAML, Open Identity Connect, OAuth 2. And Workday is a cloud-based HR, finance, and software as a service provider. I think our marketing tagline right now is HR and finance apps built for the future. And what this means to me as a technologist and on the tools and platform side of things is that we're building these new platform services using modern technologies and tools. And in a lot of our recent efforts, we've moved towards using Scala and Akka to implement platform services to build out these HR and finance systems. So why go reactive for authentication? Why not just stay the course of our traditional mechanisms? What I've been focusing on in particular is breaking out our authentication logic from our sort of traditional monolithic embedded approach to a completely standalone service that the platform would be able to leverage across many points. And in doing so, we've moved from our sort of traditional stack of using custom Java on Tomcat towards using Scala and Akka, and in some cases running with the Play framework. And in doing the system redesign, we found a really compelling case for using reactive programming. I think a lot of our initial interest in Scala was, it was an elegant way to solve our problems. It was more of a joy to write code in Scala. But for this particular use case, no one on my particular team could really refute why we wouldn't choose the reactive approach over our existing Java-based approach. So I really wanted to share those results with you guys, show and compare and contrast our previous implementation to this new implementation. So how are we going to do that? We're going to first look at our use case called delegated authentication. We're going to briefly explore the initial solution we had using a Java-based ThreadPool. And the interesting part about the solution is not when it works, but when things go bad. And so we're going to see how we can fix that using an asynchronous non-blocking model. We're going to do a quick demo, sending lots of requests at it, and see what happens. And then finally, sort of explore why this problem is so much worse in multi-tenancy models. But first, I'd like to show you the Vasa. What you're looking at here is the CAN index of the Vasa. This is a Swedish ship from the 17th century, and at the time, it had the largest broadside firepower of any ship of its class. It had 2 levels of cannons. And really, at the time, the tactics of sea battle were changing, and this sort of drove this cannon innovation. But unfortunately, shipbuilding in architecture was an imprecise science at the time. People had a rough sense for what to do, but they didn't have a precise model. So rather unfortunately for this ship, 1,300 meters into its maiden voyage, the Vasa sank. So what happened here? The sails caught a strong gust of wind, and these water level cannon decks, this innovation, they were open as the ship was leaving the harbor, and they began to take on water. And that was sort of the end of it for that. So this design that was so focused on military might sort of eluded the basic functionality, which is your ship needs to stay above water. And really what led to that is a spike in conditions, right? It was the fact that the ship was in a particular configuration and experienced just too much wind at this given moment, led to the ship completely failing. So by way of thinking about catastrophic failure in systems, I'd like to introduce our protocol that we have to implement called delegated authentication. So in this model, we have a user using one of various browsers. They'd like to log in or authenticate to our system. So we have a presentation tier that serves up some sort of login form to gather a username and password. And then that system takes those credentials and relays them on to a backend for processing. And what's interesting about delegated authentication is we don't actually store the password hashes for these users, which is actually desirable from a security standpoint. We don't really want to be responsible for those in any case. So the customer is able to configure their system to relay these credentials out to an external endpoint. So you have to send the credentials out across the interwebs, to some sort of RPC endpoint, some web service that's exposed where they've implemented an API saying, sure, we'll take the credentials and we'll check them for you. So maybe they have a few boxes configured to do that. And those boxes usually actually can't answer that question either. So they have to do a query to a database or maybe an LDAP bind to actually verify that those credentials are correct. So now you see 1, 2, 3, 4, 5 points of failure, potentially, to answer to this sort of relatively simple question, can I authenticate this user? And unfortunately, 3 of these things are really completely out of our control. We have to rely upon these systems to answer this question. So how can this fail? Well, the network routes could be slow. We could have some issue actually getting to that external endpoint. The services that are hosting their web service could become inundated with requests. This could have been sort of post-patching and they're having some issue coming back up to speed. Or the database that they're hosting is inundated with requests. It's unlikely that they're going to turn up a dedicated database just to perform this service. So maybe they carve off some small portion of an existing system, and it's just not able to keep up with the load of sending requests at it. So the initial solution that was done in Java was basically to use a ThreadPool to sort of encapsulate the amount of effort we wanted to spend attempting to make delegated authentication requests. So over here we have our ThreadPool, and we use a timed ThreadPool. So we sort of say, well, we're willing to wait X number of seconds to make these requests, and we're willing to make N number of requests in parallel, and after that we're going to cut off the request and say it failed. And I know this is not a Java conference, but I just want to give you a sense for the scope and scale of what's required, even just to make a toy implementation of this. So basically, to expose the thread pool, to instantiate a thread pool of 10 threads, to take in some parameters from the request, create a new callable, say how long you're willing to wait for it, handle the various exceptions and exceptional cases. It's a whole screen full of code, and we actually haven't even done any business logic at this point. This is all just bookkeeping to set up our thread pool. And finally, we get to our callable implementation where we can actually say, OK, we're actually going to make an HTTP request. We're going to make a GET request to this endpoint that will actually represent the customer's ability to verify the credentials. And we'll execute our GET request. And at this point right here, when we actually execute that GET request, we're going to block on that external site. So I'm a very visual learner, and I wanted to sort of imagine what does this look like in practice when things sort of break down? What happens when things begin to block? So OK, in our hypothetical scenario, one of those nodes becomes overloaded, and now it's taking 5+ seconds to respond to our request. This is a particularly nasty kind of failure. If we had it immediately fail, that would be great, because we could immediately turn around and tell our end user, sorry, we can't authenticate you right now. But we think maybe they could actually authenticate us. We just have to wait this 5 seconds for them to reply. So as a request comes in from this presentation tier, the Tomcat thread pool allocates a thread to serve it, and it spins up this thread in the Delauth thread pool, and it starts to block, waiting on that external site. And as more requests come in, they start to stack up on top of each other. We've got this timer to try to cull this behavior and limit the impact of this. But if we get too many requests flowing in too rapidly, we sort of start to see this one-to-one parity of the Tomcat threads in the container and sort of the ability to service new requests coming into the application being all tied up behind this thread pool waiting to execute. And so we need an alternate approach to this. We can't, this isn't a serviceable model, having the blocking leaking up to the Tomcat threads. In particular, once everything's blocked, waiting for Delauth to execute, then other requests for users who are already authenticated aren't going to be able to be serviced either. Those will back up blocking behind that as well. So instead, and in looking at refactoring to create a central service to handle authentication across many, many tenants and many, many systems, we especially can't exhibit the behavior where one bad actor in this system could back up the entire model. We need to be able to scale with the load that we experience. So this is where we started to look to reactive programming. And I attended a talk earlier this year. James Ward gave a great talk at the SF Scala group called Reactive All the Way Down. And I was taking Bart back to the East Bay thinking about the ideas he had put forth. It sort of clicked that, wow, this is the perfect solution to the problem we have at hand. We have to rely on these external parties to serve our requests. But how could we do so without consuming as many resources? So enter reactive DelAuth. So in this model, we have the same scenario. We have the user authenticating to the front door of our system. We have the external service that we're relying upon, the exact same external service. But now, inside the guts of our giant computer, we have Netty threads ready to service the requests. And it's dispatching those requests asynchronously using the play's default ThreadPool. And it's creating futures to block on each one of those GET requests as it sends the external request to the service. And those futures are running inside the default execution context. So we're not actually creating threads. We're not having to manage a pool of threads. And instead, we're allowing the framework to manage the futures that we create to execute that. And so it's using its own threads to do that control. So what does this look like in code? In play, we need to create a route to represent that. So for this example, we're just going to define a GET request that says we're going to invoke this DelAuth service. And the implementation for the service, we're going to have to create a controller. So we define a controller. And then we say that we'd like our action to be asynchronous. And then the actual definition of our action is we're going to extract a username and password parameter that were sent in on the request. And when we make that request, we're going to use the play WS library, which actually makes an asynchronous request. It doesn't block on the request. It returns back a future for us to wait on the return from. And so in this case, it returns a future of type WS response. And then we're using another trick here where to sort of get a better sense of control for timeout, we're creating a promise that says we're going to execute this request, and we're also going to wait in this promise for 60 seconds. And then we're going to compose those in a sequence and wait for whichever one's going to complete first. So if our external request completes first, then we'll write back the response of what the service returned. And if we haven't gotten a response within that 60 seconds, then we'll return a 500 error that we timed out. So what does that look like in contrast to the model that we saw before? So the same system that we're trying to talk to has become inundated with traffic. It's overloaded, and it's taking 5 seconds to respond. So a request comes in. We have a socket that's consumed when we make the inbound request to the server. And for a moment, the Netty thread is blocked as it has to read the HTTP request in and sort of relay those bytes and figure out how to route the action. And as you saw in the code in the previous slide, this future is created to make the GET request to talk to the external service. But what's markedly different is as soon as that future is scheduled, as soon as it's begun executing and we're waiting on it, Netty's able to immediately use that thread to start to handle other requests. It's no longer blocking and waiting for any more I/O. It's fetched all its I/O. As far as it's concerned, it's done waiting. So we have this open socket to our server, and we have the future waiting on executing and getting a response back from the external system, but we don't have any other resources consumed. And as we get additional requests coming into the system, in parallel with that first one, more sockets are created. Momentarily, the Netty thread is consumed reading the request before it creates another future once it figures out the action to execute. And then again, the Netty thread's given back. And so what's particularly interesting about this model is we don't end up with fixed amount of resources that sort of have this upper bound that are going to be consumed against. We don't have this thread pool that only has 10 threads in it, or however many threads that we have to figure out what's the appropriate number to pre-allocate. We have dimensions that we can grow in. We can create additional sockets to handle additional requests as we need, up to the upper bound of the number of file handles we can create on this particular server. And we can create far more futures in this execution context than we could threads if we were to use a threading model. Besides the fact that we don't have to know beforehand how many threads we might need, they're a much lighter weight entity. And so we can scale in both of these directions with the amount of load that we're experiencing. Also, because we're not blocked behind any particular resource in this case, let's say that our customer actually had a load balancer and they had multiple nodes able to service this request. Since we're still able to send non-blocked requests through, we have this open route to a host that's available to service our request. And maybe that's able to service our request immediately. And so by using this model, we're able to achieve much greater performance in these failure cases. So what I was curious to see is now that we had sort of two potential models to compare our previous approach using ThreadPool and the Netty-based play approach, is sort of race them against each other and see actually how they do perform in action. So we sent n requests into a simulated delegated authentication service, and we had half of the requests go to this one node that's experiencing this partial failure, so it was waiting for 5 seconds before it serviced the request, and the other half go to a node that was running quote unquote normally and returning after 100 milliseconds. So in our ThreadPool-based model, we use 10 threads, each timing out after 15 seconds. And in the async non-blocking case, we had a timeout set to 60 seconds, like you saw before. But before we could actually run the scenario, we needed some sort of tool to send lots of load at our simulated scenario. So we did some looking and found a great solution using Gatling. Gatling's a wonderful open source tool that allows you to use Scala to define load tests for your application. It uses asynchronous HTTP client and Netty libraries as well to send out those requests. And it provides a really nice DSL to write load tests for your application, a nice fluent DSL. So basically what you're able to do is define a scenario. You can define HTTP requests. So in this case, I'm making a GET request to a congested endpoint. I'm going to make sure that it returned back with a 200 status code. I'm going to check in the body of the request to make sure the string done showed up. And then I'm going to make a subsequent request to the normally performing endpoint, again, making sure it returned status code of 200, and then it returned done. I could pause for some random variation. And then ultimately, I say I'm going to send 50 requests in this model. So that'll be 100 total requests, one to the slow server and one to the normal. And I'm going to ramp up rather quickly and just send them in one after another, only waiting a millisecond to add each additional user to the system. As a bonus, it renders really colorful charts. So if you have to show other people how things are performing, at least you get that. So that's good. And the default timeout for the system is about a minute. So that's another detail in case you want to change that configuration. So we're going to first demo the blocking approach. All this is running on my laptop. So basically, we're going to run the Gatling client against the Tomcat-based implementation using the Java ThreadPool. And then sort of from that middle processing tier, we're going to send half the requests to a simulated external service that's performing normally, and half of the requests to a congested node. So let's hop over. OK, so we can see. Hopefully, you guys can see that. So we're going to run Gatling. And it sort of goes and looks and sees all the scripts that you currently have defined. So we're going to hit the ThreadPool-based approach. It asks for a couple default parameters. We can just sort of ignore them. And starts up the scenario. This hopefully shouldn't take too long. And so you can see it gives you some great ASCII stats as to what's going on. We're getting a little bit of line wrapping because my font's so giant. And then we start to see a bunch of failures fly through here. And it's done. It sent 100 requests to the service. And it gives us a nice little status report that we can go grab and throw this in our browser. So we see really big. But cool, we can get a quick indication. 70 requests made it through. 30 requests failed. And we get some quick statistics on how they executed. We see that the requests to the slow endpoint took on average about 11, 12 seconds. And the requests to the endpoint that should have responded in 100 milliseconds actually took on average about 8 seconds to respond for those that successfully completed. So if we hop back over here. So we have to make a couple quick tweaks to the Scala-based implementation before we can do the same thing. So we add another route and play, basically breaking out our existing service to call 2 different services, one to the congested service and one to the normal. And sort of we wrap our service invocation in 2 asynchronous actions and send the implicit request context along down to that so that we can pull out our parameters. And again, same code as we looked at before. It chains the 2 features together from a timing perspective. So just to be really clear, this is the exact same model, same client, except written to call the specific endpoints here. We've switched out the middle implementation for the code you just saw, and we're calling the same 2 external services. So let's see how that one executes. So we go to run Gatling. We have a scenario written to hit the reactive model. Oh, yeah. Sorry. Thank you. Silly computer science starting at 0. OK. All right. So we started the reactive model. And we see it finishes nearly immediately. We can open up the chart here, and we can see things look a lot better. We have no failed requests in this case, and actually a large number of our requests replied in under a second. So we see 100% of the requests were served. And on the average, hitting the slow endpoint took the 5 seconds as we expected. And really much nicer, much better in this case, is that it only took 100 milliseconds to serve the requests to the normal endpoint. So we were able to have direct communication to the server that wasn't bogged down because we had nothing blocking in the way. So that was fine and good for 100 requests. But we're sort of curious to see what would happen when we ramped up load against this model and serviced more requests. So in this case, initially we sent 2,000 requests in a couple of seconds and sort of saw similar failure behavior. In the Java-based implementation, over half the requests fail. And the average times are horrible. 30 seconds on the average, the slowest service. And particularly disturbing is to the service that was sitting there ready to respond in 100 milliseconds. We got an average performance time of 30 seconds talking to that endpoint. So in stark contrast to that, with 2,000 requests at the reactive node, we see, again, 100% of the requests are serviced in this case. We got sort of this throughput of like 2 times the previous one. And what's really impressive, again, is the average wait time for the slow node ticks up a little bit. We're up to 19 seconds now. But for the endpoint that's ready to respond, we get this immediate response of 100 milliseconds. And that's, far greater than the other scenario. Oh. So we wanted to, continue to play this out and send more and more traffic at the different endpoints. And look a little bit, in our scenario as to how they perform when compared against each other. So what we see here is for the reactive model. So what we're first looking at is response time by the approach for the particular node. So across the board, no matter how much traffic we sent at the normal endpoint, we always got around 100 millisecond response time, which was fantastic. For going against the block node, using the reactive approach, this beige color here, we saw a similar pattern of around 19 to 20 seconds. And then using the ThreadPool model in contrast, Again, things capped at about 30 seconds across here, whether we're talking to the normal node or the block node. And what's particularly interesting is the failure rate percent by the approach. So you can sort of see out of the gates, trying to talk to the block node, it's timing out, obviously. And we get this horrific over 90% failure rate, even with only 2,000 requests. And as we ramp up to 3,000 and 4,000 requests, the wheels completely fall off for the ThreadPool, and it's pretty much useless at 5,000 requests over a few seconds. And what's interesting here is for the reactive model, things continue to look really good up until we get to around 5,000 requests in that given few second interval. And then we actually do see a small failure rate. About 12% of the requests did fail. And going against the slow node, we saw that even higher number of requests started to fail, around 40% when we sent 5,000 requests in this interval. So you might think to yourself, what? The reactive approach can't fail. Scala can't ever let us down. But in this case, what we see is that we hit up against the file handle limit of the operating system. So we see a bunch of exceptions being thrown, too many open files in the system. So by default, your Mac has about 10,000 K limit for open files. And so as our client and our server running on the same system made 5,000 open requests and tried to service 5,000 requests at the same time, and then we had a few other background things running, we sort of tipped the system over and hit that 5,000 or hit that 10,000 number. And for the slow case, when we started to see failures in the 3,000 to 4,000 model, what we saw is that for the slow nodes, we actually hit that 60-second timeout in Gatling. So I had mentioned before that the default timeout is a minute. And while it was executing all of those requests in parallel and switching from request to request to see if they had been serviced or not, it actually did take longer than 60 seconds to service them. So this is just a side note on Tomcat configuration. I don't know if you can see this here, but basically, before we changed the setting, the reactive approach and the Tomcat approach behaved identically, whether we use a ThreadPool or we use reactive programming. And this is sort of an interesting point to consider is, we're talking about mitigating failures when we're communicating with external partners, potentially people running servers outside of our control. And so what we had to do is we had to greatly increase the accept count on that Tomcat service. We had to bump it up to I think I have 10,000 in here. If you run a vanilla Tomcat out of the box, it can't accept that many connections in parallel. And basically, it starts to reject all the inbound requests, and you get, again, identical failure rates. So, while this is a much better solution in the generalized sense, and likely you'll be consuming services configured to sort of, work at internet scale, if you are talking to a smaller or federating with a smaller entity, you might have to make sure their servers are properly configured to handle that many requests in parallel. So finally, I just want to talk a little bit about how this failure potential compounds in multi-tenancy. As we saw in the previous examples, we had one processing backend, and that went out to one customer site. But in reality, our systems are multi-tenanted, and we have one processing backend that might host, tens or 50s of tenants all in parallel, and need to share those same system resources. And so if that happens, whether we use a ThreadPool per tenant or some other model to mitigate that, if we do have this case in which the blocking can leak up to the Tomcat threads, then we really need to use an alternate approach to sort of defend against this failure rate. So, again, this one service going down and experiencing a high load to authenticate customers to tenant A could have this ripple effect if we don't have some way to compartmentalize that failure. So in closing, just wanted to highlight that we didn't design to say how can we make the service go from 4 seconds to 3 seconds? Or how can we use less memory? Or how can we do X? What we focused on is how can we compartmentalize failure? And when we did that, when we were able to achieve that, we sort of experienced an increase in performance as a side benefit. The Scala play-based approach allowed us to focus on our business logic and security details. As you saw from the 2 code examples, we had an entire page of code just to establish a ThreadPool and some bookkeeping and all the boilerplate surrounding that. And in the play approach, we were able to focus directly on the implementation of extracting parameters from one side and sending on our requests to the other side. And what we found, the real key to performance in this model was that we left open pathways to the responsive nodes. So instead of blocking on this thread pool and not knowing whether or not we could get a response back from the slow external site or not, having the ability to continue to service new requests as they came in is really what yielded the greatest performance. And that's where we saw the ability to continually get this 100 millisecond response time from our node that was ready to service requests, because we didn't have to stack up or wait behind these nodes that were slower. So, final thought here is that great tools and techniques allow you to test your ship before it leaves the port, and the right frameworks and architectures ensure that it doesn't sink on the way out. Thanks.